All right, so we're going to look at rates of change in an exponential and logarithmic functions. We're going to basically focus on exponential functions. Now, we've dealt with exponential functions, but specifically, an exponential equation is written in the form y equals a, this is the general form, times b to the power of x, where a is what we call the starting amount for whatever you're dealing with, and b is the multiplying rate or multiplying factor. All right, so that's a simple, and we've dealt with exponential equations, but that's a simple way that they look. What we're going to come up with is, well, finding the rates of change, estimating the rates of change, in some cases. So example 1, for a 1600 gram or of a radioactive substance with a half-life, which we've talked about, half-lives and doubling times of 8 hours. The amount remaining is given by the formula m equals 1,600 times 0.5 t over, that's an 8 there in the denominator, where m is the mass and t is the time. Determine the average rate of change between day 1 and day 2. All right, so we're first off looking at the average rate of change, which we haven't done much in a while. All right, now that is referring to when we're looking at slope. Now, I will tell you a couple of things, is that our half-life formula here, I underlined here, hours, but we're looking for the change in between day 1 and day 2. And so what we need to do is make sure we're in the right units here, because as I've mentioned with both the doubling times and the half-life formula, the t and the 8 have to be in the same units. So for day 2, that's 48 hours later. So everything's got to be in hours, because that 8 is in hours. And day 1 would be 24 hours later. So that's the first thing. Get our units the same. Now, the average rate of change is when we're just finding the slope. So this is our m function. So m of our first or our second x value, which would be 48, minus m of our first x value, which would be 24. That's our y2 minus y1, if you will, from grade 9 math. Subtract x2 minus x1, which would be 48 minus 24. All right, so over on the side here, what I always like to do is figure out this stuff, make it less confusing. So I'm going to put 48 into that formula. So in for t goes a 48. So 48 divided by 8 is 6. 0.5 to the power of 6. And then times 1,600. And I get 25. All right, then I'm going to put in 24 in for t into our formula. So I got t divided by 24 divided by 8, which is 3. So 0.5 to the power of 3 times 1,600, and I get 200. All right, so now I can place those values into my formula. So I've got 25 minus 200. And then in the bottom, 48 minus 24 is 24. All right, so I take my 25, I minus 200, and then I divide by 24, and I get negative, which I knew was going to happen, 7.29. And that means our average rate of change here is that the substance we're dealing with, the radioactive substance, is decreasing because it's a negative sign at a rate of 7.29. What is the substance? Grams, okay, per hour between day 1 and day 2. That's what that value means. Can't fit that in there, but there we go. Now we get to B. Estimate the instantaneous rate of change after day 1. Instantaneous rate of change and estimate. All right. So again, day one, this formula is in hours. So we're talking about 24 hours here. All right. And so since we are estimating, we have our instantaneous rate of change, which again is different. And that's where we're going to take M of, after day one here, of 24. And because we're estimating, we'll add a little bit. So 24.01. Subtract M of 24. Whoops. And again, this is where we're combining our two formulas that we had before, where our limit, instead of an H value of 0, we'll just put in a 0.01 because we're estimating. All right. And again, we're going to divide it by 24.01. Subtract 24. All right. So again, we're combining our two formulas. But again, we're finding the instantaneous rate of change. Now, I already found M at 24. Just up there. And that was 200. Okay, now I also have to find M of 24.01. All right, so again, I'm going to plug T equals 24.01 into the formula. So I'm going to have to divide that by 8. And then I can take 0.5 to that number. Okay, and then times by 1,600. And I end up with 100, going to two decimal places here, 199.83. All right, and so I can plug my values in. All right, so I have my 199.83, subtract 200. And down the bottom again, let's see, well, 24.01 minus 24, we're down to 0.01. And, well, let's see, I do a little bit of math here, take my 199.83, subtract my 200, and then divide it by 0.01, and I end up with minus 17. And so what that is telling me is that the substance this time out, or at this instant, again, it's negative, so it is decreasing at a rate of 17. Again, our mass is in grams. Our time is in hours after day one. There we go. So the substance is decreasing at a rate of 17 grams per hour after day one. Where between day one and day two, it's only 7.29 grams per hour. So this material is wasting away a lot quicker early on, it appears. All right, so let's try something a little bit different here. Abby invests $1,400 in a savings account that pays 7.5% annually, compounded annually. How much is in the account after 3 years? All right, so we can come up with a formula here. All right, and just given the fact that, again, when you're dealing with an exponential equation, it's going to be in the form y equals a times b to the power of x. And in this case, our a, for example, 1 was 1,600 grams. That's what you started with, the amount you started with. 0.5, it's its multiplying rate, as in it is cutting in half each time. What we're going to have to do this time is come up with our own equation. And so the amount, start off with the A here. We start off with $1,400. That is our starting amount. Now we get to the multiplying factor. Now that's a little bit different. Here, I'm going to do this over the side. So again, our starting amount, 1,400. But our multiplying factor can be calculated by looking at percentages. All right, is that it pays 7.5% annually. So you have 100% of your money, but after 1 year, you've gained 7.5%. So in total, after 1 year, you have 107.5% of your money. It's increased by 7.5%. So the 100 refers to you still have all that money, plus you've got 7.5% more. Now, here's the thing is that percent is useless in math as a calculation. You got to convert it to a decimal. And when you're converting percent to a decimal, you just simply divide by 100. And so if I take 107.5 and I divide it by 100, I get 1.075. And so that is my multiplying factor. There we go. So my multiplying factor is 1.075. And again, it's always going to be to the power of x, where annually, so x, because it's annual, x is the number of years. All right, so now we get to this. B, we have our formula. Estimate the instantaneous rate of change in the account after 3 years. So again, we're finding the instantaneous rate of change. And after 3 years, so I'm going to have to take my amount and figure out 3 years plus a little bit. And again, subtract my amount, which is at 3. And divide it by, of course, my 3.01 minus 3. All right, so what I like to do is go over on the side here and figure stuff out. So my A of 3 here, what I'm going to do is wherever there's an x in that equation there, I put in a 3. So I have 1.075 to the power of 3. And then multiply by 1,400, and I get 1,739.22. All right, I'm going to do the same thing. I'm going to plug in my value, x value of 3.01. And I end up with 1,740.47. All right, so now I'm going to plug those values in. All right, so I got my 1,740.47, subtract 1,739.22. And then I'm going to divide that. Of course, if I take 3.01 minus 3, well, that's just 0.01. All right, so I do a little bit of math here. So let's see here. Take those numbers up top. I subtract them. And then divide by 0.01. Oh, odd. Okay. I actually get right on 125. So that's telling me this, is that the money in the account it's a positive number, so it is increasing at a rate of $125 years, we're in years per year, after 3 years. There we go. So that is the rate at which the account is increasing because you're making money and interest. All right, so let's try another one of those here. Let's see, a little something different. I'll throw a little something different at you. Let's go with we don't have time for one more here, so I'm going to go with example 4. All right. The population of an ant colony is decreasing at a rate of 16% a month. Good. The current population of the ant colony is 850. Write an equation that models the population of the ant colony. All right. So again, looking at coming up with an equation. So we need 2 values. We need our little a here, which is our starting amount. And it already tells us flat out that we start off with 850 ants. Now to find our multiplying factor. Now you start off with all the ants, unfortunately. You get 100% of them. But where they're decreasing, thank goodness. So I'm going to do a subtraction here. And they're decreasing at a rate of 16% per month. And so if I take 100% and I subtract 16%, I get 84%. And as I mentioned before, percent is useless to us in terms of calculations. We actually need to convert it to a decimal. So I divide by 100 and I get 0.84. All right. So now I can write down the equation. The amount of ants, A of X, I guess we should say, function notation, is equal to my starting amount, which is 850, times my multiplying factor, which is now 0.84, and to the power of x, where x is the number of months, because we're at percent a month. So number of months. All right. Now it says B. Estimate the instantaneous rate of change of the ant colony when there is 500 ants. Okay. Here's a little bit of a tough part here. When there is 500 ants. I don't know when there's 500 ants. Before, we were given the value, right? It was after 3 years. Or what was the other one? After day 1. I don't know when there's 500 ants, so I'm going to have to figure it out. So I'm going to take my equation here, my exponential equation. The amount of ants is 500. It's equal to 850 times 0.84 to the power of x. I'm going to have to find out when there is 500 ants first before I find the instantaneous rate of change. All right, so I'm going to have to solve for a exponent, which means I'm going to have to use that log function. But before I do that, I'm going to divide both sides here by 850. All right, so we get 500 divided by 850, 850 divided by 850. So those are divide each other out. I take 500 and I divide it by 850. I end up with, let's see here, 0.588 is equal to, again, I have my 0.84 to the power of x. Let's go with this instead. There we go. All right, and again, since I'm solving for an exponent, I'm going to take the log of both sides. And of course, when I take the log of the right-hand side, again, I'm going to use that log rule here. So when I take the log of it, the exponent comes down in front, which now is just the x. And then I have the log of 0.84. All right, just simplifying things here. The log of 0.588. It's a small number, so it's it ends up being negative 0.231 is equal to x times the log of 0.84. And it's also negative, so we get negative 0.076. All right, and let's see here. Last step, finding out x anyways. I'm going to divide by this negative 0.076. And so those divide each other out. And so my x value is equal to, let's see here, I get 3.04. And again, this equation is in terms of months. 3.04 months. Okay, so if I'm going to now estimate, now I can move on and estimate the instantaneous rate of change at 3.04 months, which means I'm going to take my amount function. Oops. There we go. And I got to go a little bit above 3.04, which would be 3.05 minus the amount at 3.04. All right, and of course that is divided by our x2 minus x1, which in this case is 3.05 minus 3.04. All right, so now I'm going to do the same thing I did before. I'm going to go over here on the side, and let's see here, the amount at 3.05. So I'm going to plug that amount into my equation. 3.05, or sorry, 0.84 to the power of 3.05, and then times that by 850. I get 499.43. And I'm also going to do the same thing with 3.04. And let's see, 0.84 to the power of 3.04, and then times 850, I get 500.3. All right. So now I'm going to plug those in. So my instantaneous rate of change, estimation, of course. That's why we're not doing that limit stuff. Let's see here. So I got my 499.43. Subtract my 500.3. Of course, divided by, take my 3.05 minus 3.04. I get my 0.01. All right, and the grand total here, let me do that number, 499.43, subtract 500.3, and then, of course, I got to divide that by 0.01, and I actually get a nice whole number again, negative 87. Oh, Crosby. So what is that saying? That the ant colony is, and again, this is a negative sign, so it is decreasing, which we already knew, right, in the question. It's decreasing at a rate of 16% a month. But specifically, the amount is it's decreasing at a rate of 87 ants per, again, time is in months this time out, per month, after 3.04 months. There we go. So again, in this situation, we actually had to find out what the time was for the instantaneous rate of change before actually figuring it out. And again, you got to watch out when you're creating your exponential equation. If you're decreasing, then your multiplying factor is going to be less than 100%. If you're increasing, then it is going to be over 100%. And in terms of a decimal, if your rate's increasing, your b value is going to be over 1. And if you're decreasing, your b value is going to be under 1. And there we go.